Chapter 1.5.1 Service. In Kubernetes, services are used to expose network applications running on one or more pods in a cluster without the need to modify existing applications. Services make sets of pods available on the network so clients can interact with them, even if the pods are created and destroyed dynamically by deployments in response to the desired state of the cluster. Each pod has its own IP address, and due to the ephemeral nature of pods, front-end applications may need to identify and keep track of the IP addresses of back-end pods, providing functionality within the cluster. This is where services come in, acting as a discovery mechanism that allows front-end pods to connect to and utilize the functionality of back-end pods, ensuring seamless communication within a Kubernetes cluster. Services in Kubernetes. The Service API in Kubernetes allows users to expose groups of pods over a network by defining logical endpoints and policies for accessing them. This abstraction enables decoupling between front-ends and back-ends, allowing front-ends to remain unaware of changes in back-end pods. Services can be defined using selectors, and there are alternative ways to define service endpoints using services without selectors, or by using ingress for HTTP workloads to control web traffic. The Gateway API provides additional capabilities beyond ingress and service, allowing users to configure network service access in their cluster. Cloud-native service discovery in Kubernetes allows applications to query the API server for matching endpoint slices, which are updated whenever the set of pods in a service changes. For non-native applications, Kubernetes provides methods to connect to back-end pods using network ports or load balancers. Overall, service discovery mechanisms in Kubernetes help workloads find and connect to their desired targets. Defining a service. A service in Kubernetes is an object that allows you to create, view, or modify service definitions using the Kubernetes API. This is typically done using tools such as kubectl to make API calls. Services can be used to publish TCP listeners for pods with specific labels, assigning them a cluster IP address that is used by the virtual IP address mechanism. Services can map any incoming port to a target port and support multiple port definitions for a single service. Services usually abstract access to Kubernetes pods thanks to selectors, but can also be used without selectors to abstract other kinds of backends, including those outside the cluster. Custom endpoint slices can be created to link to services without specifying a selector. When creating endpoint slices, it is important to follow certain guidelines for labeling and IP address restrictions. Endpoint slices are objects that represent a subset of network endpoints for a service. Kubernetes automatically creates new endpoint slices when existing ones reach a threshold of 100 endpoints. The Endpoints API is being replaced by the Endpoint Slice API, which offers more flexibility in handling overcapacity endpoints and application protocols. Kubernetes limits the number of endpoints that can fit in a single endpoints object to 1,000. When this limit is reached, Kubernetes truncates the data in the endpoints object. Multiple port definitions can be configured on a service object, with each port having a unique name following specific naming conventions. The App Protocol field allows you to specify an application protocol for each service port, providing richer behavior for protocols that are understood by the implementation. Overall, services in Kubernetes play a crucial role in managing networking within the cluster, allowing for the seamless communication between pods and external services. By understanding the various features and capabilities of services, developers and administrators can effectively deploy and manage applications in a Kubernetes environment. Service type. Kubernetes offers various service types that allow you to expose a service onto an external IP address, making it accessible from outside of your cluster. The available types are cluster IP, node port, load balancer, and external name. Cluster IP exposes the service on a cluster internal IP, making it reachable only from within the cluster. This is the default type used if a type is not specified. To make the service accessible from the public internet, an ingress or gateway can be used. Node port exposes the service on each node's IP at a static port. Each node proxies that port into the service, allowing you to set up your own load balancing solution or expose individual nodes' IP addresses. Load balancer exposes the service externally using an external load balancer. Kubernetes does not provide a load balancing component, so you must either provide one or integrate your cluster with a cloud provider. External name maps the service to an external DNS name without proxying any traffic. It is useful for redirecting requests to a specific host name without exposing any functionality. The type field in the Service API is designed as nested functionality, but you can define a load balancer service by disabling the load balancer node port allocation. You can also choose your own cluster IP address by setting the .spec.clusterIP field or specify a specific port number for node port services. To avoid collisions when assigning ports to node port services, you can reserve node port ranges or configure custom IP addresses for serving node port services. You can use the Yash Nodeport addresses flag for kubeproxy to specify particular IP address ranges considered as local to each node. For a service of type load balancer, the actual load balancer creation is done asynchronously, and the cloud provider decides how it is load balanced. You can also specify a load balancer IP for the load balancer, but note that the .spec.loadbalancerIP field has been deprecated in Kubernetes v1.24. Health checks for load balancers are essential, as they determine which server should receive traffic. Load balancer health checks are critical for supporting the external traffic policy field for services. In Kubernetes v1.26, a feature allows load balancer type services to use different protocols for multiple ports. You can also disable node port allocation for load balancer services by setting spet allocate load balancer node ports to false. Specifying the class of load balancer implementation and setting the IP mode of load balancer status are additional features introduced in Kubernetes v1.24 and v1.30, respectively. These features allow you to customize the load balancer behavior based on your requirements. An internal load balancer is sometimes necessary for routing traffic within the same network block. Services of type external name map a service to a DNS name, allowing you to redirect traffic at the DNS level instead of proxying it. Overall, Kubernetes offers a range of options for exposing services externally, allowing you to customize the behavior based on your specific needs and requirements. Headless services. A headless service in Kubernetes allows a client to connect directly to individual pods without any load balancing or proxying by the platform. By setting the cluster IP address to none in the service configuration, a headless service does not allocate a cluster IP, bypasses kubeproxy handling, and reports endpoint IP addresses of individual pods via internal DNS records. Clients can connect to whichever pod they prefer directly. To define a headless service, the service type is set to cluster IP and the cluster IP field is set to none. How DNS is configured depends on whether the service has selectors defined. For headless services with selectors, endpoint slices are created in the Kubernetes API to point directly to the pods. For headless services without selectors, DNS records are configured for either external name services or all IP addresses of the service's ready endpoints. When defining a headless service without a selector, the port must match the target port. This allows for more flexibility in connecting to pods without the need for load balancing or virtual IP addresses. Discovering services. Kubernetes offers two primary modes for clients to find a service within a cluster: environment variables and DNS. When using environment variables, the kubelet adds variables for each active service, such as svcname service host and svcname service port. It is important to create the service before the client pods to ensure their environment variables are populated properly. Kubernetes also supports variables compatible with Docker Engine's Legacy Container Links feature. Setting up a DNS service through an add-on, such as Core DNS, is recommended for Kubernetes clusters. The cluster-aware DNS server watches the Kubernetes API for new services and creates DNS records for each one. All pods in the cluster should be able to resolve services by their DNS name. DNS can also support DNS-SRV records for named ports, allowing for queries to discover port numbers and IP addresses. The Kubernetes DNS server is the only way to access external name services. In conclusion, Kubernetes provides environment variables and DNS as primary methods for clients to find services within a cluster. Environment variables require creating services before client pods, while DNS setup through an add-on enables automatic resolution of services by their DNS name. DNS SRV records are supported for named ports, and external name services can only be accessed through the Kubernetes DNS server. Further details on external name resolution are available in the Kubernetes documentation. Virtual IP addressing mechanism. The text discusses various mechanisms provided by Kubernetes to manage traffic routing and exposure of services with virtual IP addresses. It explains how you can control traffic routing to healthy backends using fields like .spec.internal traffic policy and .spec external traffic policy. Additionally, it introduces the .spec.traffic distribution field, which allows you to express preferences in traffic routing, such as routing to topologically closer endpoints for optimizing performance, cost, or reliability. This field is optional and requires enabling the Service Traffic Distribution feature gate. The text also mentions the prefer close value supported in Kubernetes 1.3.1 for routing traffic to topologically proximate endpoints. It highlights the importance of session stickiness for passing connections from a particular client to the same pod each time, and suggests configuring session affinity based on the client's IP address. Overall, the text provides insights into managing traffic distribution and handling session stickiness in Kubernetes services. Kubernetes Services allows external IPs to route to cluster nodes, exposing services on those external IPs. When network traffic arrives with the external IP and port matching the service, Kubernetes routes the traffic to the service's endpoints. External IPs can be specified for any service type. Kubernetes does not manage allocation of external IPs. This responsibility falls on the cluster administrator. An example is provided for accessing a service named My Service on external IP 198.51.100.32.80. Service is a key resource in Kubernetes API. More information on the Service API object can be found in the documentation.